Okay, hello everyone. Welcome to Veolia Water Technologies webinar, Biological Processes for Refineries. We're going to go ahead and get started here. You have two audio options through your phone or through your computer. Everyone is already on mute, so don't worry about muting your lines. Ask questions in the question section, and I'll give them to Bridget at the end of the webinar. Use the panel on the right to ask your questions. If you're having issues with your computer audio, use your phone audio to dial in, and that should clear that up. At the end of this webinar, we'll have a quick 3-question survey. Please take it, and this will inform our content for future webinars so we can deliver the best information possible for your needs. Just an FYI, before I introduce our speaker, I just want to tell everyone that we have a seminar coming up in Palm Springs, California in October. This is a one-day seminar. It will include topics like water treatment for the various streams in refineries to improve efficiency and reduce cost. We'll talk about the latest technologies for water treatment challenges like deoiling, removal of scale formers, organics, TDS, plus a few new digital solutions that use big data to optimize water treatment. And then here's the website where you can sign on and sign up for this event in Palm Springs, California. Let me introduce our speaker. This is Bridget Finnegan. She's been with Veolia Water Technologies for 5 years. She's a process engineer, and she specializes in biological treatment systems and disk filtration. Bridget has her bachelor's in chemical engineering from Penn State University and her master's in water resources and environmental engineering from Villanova University. So Bridget.
Thanks, Dennis. So the beginning of this presentation, why are we even talking about this? Because refinery managers want to cut costs and add operational efficiency to their water treatment. And also some companies have a special emphasis on becoming better environmental stewards, and biological treatment processes are a good way to do this. So what am I going to be talking about specifically? Moving Bed Biofilm Reactors, so MBBR. It's a proven process for refineries and oil and gas applications. It degrades common contaminants from refineries. It can be used in greenfield or brownfield applications, and it's very cost effective and compact. So my overview for today is I'm going to talk about biological treatment as a whole. What is it? How does it work? Then I'm going to talk specifically about the MBBR process, and then more specifically about refinery applications for the MBBR process, and finally some case studies and a conclusion. So biological treatment, how does it work? So biological wastewater treatment uses living microorganisms to destroy or transform pollutants. So that means that these little creatures use human trash, or pollutants as we would call them, contaminants, as their treasure. So they use them for food, for energy, and also the energy necessary for their reproduction. So microorganisms are invisible because they're so small. They are, you can see they're 0.001 to 100 microns in diameter. So to give you an idea, bacteria have been around a lot longer than we have as a race, and they are also significantly more populous. So they have about, you can see, about 100,000 times more of a population than human beings on the planet. So this slide is just a slide to show like the different kinds of species and the variety of species that are used in wastewater treatment specifically. So we aren't growing just one kind of bug. We're growing all these different species to do all different things in the most efficient way possible. So why do we care? What would we use biological treatment for? One is the removal of ammonia. Ammonia is a nitrogen source that can cause eutrophication in the receiving stream or water body. Ammonia also increases chlorine demand. So if, for instance, using like you're using chlorine to disinfect, you have to remove the ammonia before the chlorine becomes an effective disinfectant. It also increases the oxygen demand for a similar chemical process, that it has to be oxidized first. And it is also directly toxic in high concentrations. Organic carbon and cyanide are both toxic, can be toxic, and they also increase the oxygen demand. So if that water with high COD, we call it, organic carbon, is put into a receiving stream, it would deplete the oxygen supply, and then the fish die, and anything that needs oxygen within the stream would die. Nitrite also has an oxygen demand a little bit less than ammonia, but still there, and it is a direct health concern, that it can be a health concern for fish just in relatively low concentrations. And then nitrate is also a nutrient source that can cause the growth of algae in the receiving stream. So this is a little diagram of what is kind of happening. So there's a happy bacteria in the middle. From the top is coming a source of organic carbon into the bacteria, and the bacteria uses it in two ways. The first way is the biosynthesis, so it sort of reproduces and has another form of biomass, or has additional biomass that can be wasted, and then it respires for energy, and then it, similar to us, reduces carbon dioxide, or if it is using nitrate, it will release N2. So for a different kind of bug that removes ammonia, it's an entirely different species, and there's a variety of species that do both of those processes. But this kind of bacteria, the ammonia takes up ammonia in a source of inorganic carbon, which is usually CO2, and it has the same needs, so to speak. So it has the biosynthesis and the respirations, but because it's using ammonia as its energy source, the oxidized form of ammonia is then NO2 or NO3, depending on which stage of the nitrogen is taken up. So this is sort of an overview of nitrogen removal if you have an ammonia limit in your effluent, or if you're just trying to remove all of the nitrogen to lower TDS or another reason. The first stage is called nitrification. So you see on the bottom left of the screen here, there is ammonia, and it is oxidized first to nitrite and then finally to nitrate, and that's the most oxidized state of nitrogen. And this is an aerobic process. You can see the bubbles going up in it. And then the next step is called denitrification, where it takes the nitrate and it deoxidizes it. So it takes an oxygen off, so it becomes nitrite, and then finally to N2 gas. And N2 gas would bubble out of the system and be removed. So there'd be no nitrogen left. This is an anoxic process, so the COD is a needed food source for that step. So that's biological processes, and now we'll talk about the MBBR specifically. So MBBR, as I mentioned, stands for Moving Bed Biofilm Reactor. It was invented by a company called Anox Colness, that Veolia acquired a number of years ago. It uses these pieces of what we call media or biomedia or carriers as sort of stages to have biofilm form. We'll talk about what that means later. It's a mixed reactor, and the media is retained within the reactor, so it's not ever wasted. So the characteristics of an MBBR, Anox Colness that Veolia acquired was the first one. It's the inventor. The inventor of the MBBR started this company. He now still works for Veolia as a consultant. It biologically treats carbon, nitrate, ammonia, same thing, using the biomass on the moving carrier. It's a continuous process. It's just a flow through tank. There's no backwashing, so it's pretty simple, and it's also compact with a small footprint. So it's a super simple system. There's really only three elements. The first is the biomedia, as I mentioned, or media or carriers. There's these little plastic, they look like wagon wheels, and there's literally millions of them in the tank as stages for the biofilm growth. There's an aeration system, or if it's an anoxic process, as in denitrification, there's a mixer. So the pieces of media have to be continuously mixed. That's why it's a moving bed, because the bed is moving, by either of these components. So if it's an aerated system process, we would have these aeration grids on the bottom to both provide oxygen and keep the media moving. And then the third component is the sieve, which is just protecting the media from escaping the tank. It's on the effluent of the reactor. So what is a biofilm? A biofilm is a group of microorganisms and their extracellular products attached to a surface. So we have one of our experts likes to say that if you don't brush your teeth for a long time, you have a biofilm develop on your teeth. So if you're wondering, so it's just sort of slimy and it can actually do some damage. That's why we brush our teeth, to prevent the biofilm growing on them. So if you can picture on the far left here is the biomedia, so this piece of plastic, maybe one of the sides of the wagon wheels, and then the biofilm grows on that. So those are all little cells of bacteria that are developing in various thicknesses along this piece of media. So the bacteria would take up their nutrients and food. So take up nitrogen, phosphorus, COD, and the oxygen if it's an anoxic or aerobic process. And there's also in the water some TSS typically. Sometimes it's inorganic, sometimes it's organic, but in any case, it can get lodged in the biofilm. And although that is sometimes troublesome in like a high TSS would be troublesome in certain biological processes, one of the advantages of the MBBR is that it can handle a high TSS without any issue because of the sloughing, which I'll talk about in a little bit. But so the biofilm might also include this inorganic TSS. But once the nutrients are taken up, it exhales, so to speak, the CO2 and the H2O, and then the reaction is complete. So as the biofilm develops and gets thicker, they're all making more biomass, and it's sticking more to the media. So it the underside of the biofilm, like in the thicker portions, are not getting the oxygen and the nutrients that they need. So this would decrease the efficiency of the treatment process because not all of the cells have access to the material that they need or are able to remove the contaminants that are in the water. But the MBBR, because the media is constantly mixed, has a sloughing action. So it's self-regulating because the media is moving, that this biofilm is sort of being knocked off quite naturally in the moving process, and as they run into each other or run into the wall or just move around, that the biofilm is released, which keeps it thin enough so that all of the nutrients and food can get into the most active biofilm. So this is a footprint comparison based on a study that we did. As you can see in the bottom there is what we could call conventional activated sludge, the AS, and sedimentation, which is just a large clarifier. And you can see that the MBBR plus active flow is the most like footprint efficient, so to speak. It's the smallest footprint. But even if you use the large clarifier, that it's still half of the necessary footprint for the activated sludge. So as I mentioned, a pure MBBR means there's no activated sludge involved, that it just goes from reactor to reactor and to the solid separation step. So it can be separated into several stages. If you have, for instance, to do ammonia removal or even nitrogen removal, then you can have one tank be a COD removal tank, a different tank be an ammonia tank, like an ammonia removal tank, and so on and so forth. And it just easily separates them into stages, and they don't have competing like inhibitions because of the competition of the other kind of bugs. So the MBBR can handle a variety of loads, or variation in loads. It's easy to operate. There's no recycle of sludge, which is very common in activated sludge systems. It can use the same chemical treatment as an activated sludge, the same pre-treatment. It can be used as pre-treatment to an activated sludge. And then it also can handle toxic wastewaters much better than activated sludge. So a BAS system, or biofilm activated sludge system, combines sort of both of the MBBR and an activated sludge system. That's what you can see the schematic on the bottom there. It's used in industrial applications mainly because that's where you get very high strength wastewater, and also slowly degradable, sort of what we would call nastier wastewater tends to be found in industrial settings such as refineries. So BAS is a very common system in refineries. So the MBBR can be put in front of the BAS system in order to upgrade an existing activated sludge system. And it can be used to remove organic matter to help the activated sludge system concentrate on the ammonia removal. So there are over 1,000 MBBRs built by Veolia or Annex colonists in the world. We just passed that threshold last year, and we have many in oil and gas. We have over 30 installations, about 30 installations probably in the oil and gas industry. So if you're looking for a modular solution, we have what we call the MBBR pack. It is a two-stage MBBR. Inside of that container you see. It comes with a blower if it's an aerobic system and the necessary aeration grids on the bottom there, and then its own control system. So if you're looking for a plug-and-play system for a small flow or a small load, then the MBBR pack might be a good solution. So where would we put an MBBR system in a refinery? So it can be put in a greenfield, just if you're building a new facility. It can retrofit an existing facility or improve its capacity. If you need just BOD removal or BOD and nitrogen removal, biological processes can remove selenium and in forms of selenate and selenite. It can treat the POTW wastewater if you're using that as your source water, or if for sanitary wastewaters, MBBR can be used as well. It's often used before discharging to the environment to treat the wastewater of a refinery. It can also be used in reuse scenarios to increase the efficiency of that process. So this is kind of like a generic schematic of the waste streams that would be in downstream oil and gas applications. So you could put the MBBR after the primary DAF. You could put it to replace the activated sludge system. You could put it after the activated sludge system in order to polish it. Or you could make the activated sludge system in what is called a IFAS or high BAS. It stands for integrated fixed film activated sludge, which means you have an activated sludge process and then you put these carriers in the this biomedia into the activated sludge process to help it remove either ammonia or more efficiently the COD. So these are the different configurations for those options. The MBBR standalone, you can see as many stages as you want, each tank individually standing, and then the BAS or the MBBR is sort of a pre-treatment to the activated sludge, a tertiary treatment to a lagoon, or MBBR in the activated sludge system for a high BAS. So what are the key benefits for refineries? Probably the most attractive one is the low capex and opex for an MBBR. There's no solids recirculation with wasting, so that saves a lot of trouble for the operators especially, and it also improves the settling. MBBR improves the settling characteristics, so that's makes it just easier to operate. It's non-hazardous in nature. We're basically just putting the environment into like we're sort of doing what the environment would have to do, but inside a tank so that the environment doesn't have to do it. It's a compact footprint, and as I said, it's very easy to operate, so it needs little care and maintenance. So here's some case studies for some oil and gas applications. The first one was a refinery that we had an MBBR in for a number of years, and we decided to do a study to see if it was removing benzene and phenol. So you can see that the SALR, which is the surface area loading rate, there in pink, varies greatly for the which is basically like the load on the system is changing pretty dramatically throughout the test. And you can see the effluent phenols is on the right there. The scale is on the right, and then the influent scale is on the left. I think the numbers are, this is a little bit easier to see. So the COD scale is on the left there, and the feed, as you can see, it's around 1,000, between 800 and 1,000. And then at the bottom, the R2 is the effluent of the MBBRs. So here's the results of that study, that the phenols were always below 14 micrograms per liter, and the benzene was always non-detect in our studies. So we can say that yes, MBBRs do successfully remove phenols and benzene. So this is a Borger refinery, is a long-term project for us, or rather, it's a project that has been installed for a long time. The plant was upgraded in 1999, so about 20 years ago, to improve the COD removal efficiency across its already existing activated sludge. So they needed to start nitrifying and removing ammonia, and also they were having a large variation in load, and the activated sludge system wasn't responding as they needed it to. So this is an aerial view before Google Maps existed, if you can remember that time. The clarifiers here on the left were the existing ones in the activated sludge system, and there's one large MBBR reactor that is feeding 3 activated sludge systems. And yeah, they were very happy with our design. So the design flow was 20,000 meters cubed per day. So in America, no one knows what that means. It's about 5.2 mgd or 3,700 GPM. And you can see the BOD and COD loads there. So this was, we did an evaluation like after 10 years of performance, how would it do? So now it's 2019, we're due for another study, but it you can see that the load did vary throughout the 10 years, but the effluent concentration continued to be quite good. So this is a slide to show like the variability of flow. So the maximum flow is about 20 plus more than 20% higher than the design flow, which might be a problem for other systems, but the MBBR continued performing quite well. And this is showing that the MBBR took off the vast majority of the COD load. So that red line is the MBBR, and then the activated sludge effluent is the green line. So the MBBR would take the initial shock of the highest, easiest to degrade COD load, and then the activated sludge would polish it off, whatever took a longer time to degrade. This you can also tell too that the activated sludge was doing the nitrification while the MBBR was taking out the COD, because you can see that some ammonia is removed in the first stage reactor, probably through assimilation processes, whereas the activated sludge system took off the ammonia. So this was a very successful BAS process. So this is a picture of the media. This is K1 media, which is sort of the first one Anox colonists came up with. We're now on K5, and it has more surface area. The new pieces of media have more surface area than these ones do, but the K1 is extremely robust. That piece is broken just for the sake of the photo. That despite the fact that they covered in oil from the refinery wastewater, they are still working very efficiently. So the conclusion we can draw is that MBBRs can be operated more than 10 years and now more than 20 years without making changes to the aeration grid and media or sieves. So this is very good news for the owners, and that the performance didn't deteriorate, it actually improved. This adding an MBBR improved the sludge settling, so the clarifier performance improved, and then it could handle a shock load and recover within a week. So this was a nice project for us. So some key takeaways is that the MBBR is a proven process for refinery and oil and gas applications. It efficiently removes COD, ammonia, and nitrate. That can also remove trace contaminants such as total selenium, benzene, and phenol down to microgram per liter levels. There can be different configurations to meet the local needs. It's very simple to operate. There's no clarifier or sludge recycle to manage, and it provides a compact and cost-effective solution. So reminder to sign up for the Veolia Water Technologies one-day seminar in Palm Springs, Thursday, October 10th. It's called Water Management Solutions for Oil and Gas Companies. So with that, I'm gonna start fielding the questions. So will today's PowerPoint be made available to webinar attendees? Yes. So how much smaller will an MBBR be when compared to a conventional aerobic reactor? So yeah, so a conventional aerobic reactor is what I've been referring to as activated sludge. That is an aerated reactor, and I had a slide much earlier sort of making it a comparison that we did. It will vary based on oh, there, I passed it. It will vary based on local needs and like temperature and things of that nature. But this is the study that we did to ask ourselves that exact question. So depending on what kind of solid separation you use, it can be, the most it would be in this situation would be about 50% smaller. So the lifetime of the biomedia, we have an installation that's been in, an anox colonists started about 30 years ago, and that media has not had to have been replaced yet. So at least 30 years. It doesn't degrade over time. It's plastic. So yeah, it's made from virgin HDPE. So it hasn't degraded that we've seen yet. So there's a question, what is the typical MLSS in an MBBR? So this is actually a question that we, that is for an activated sludge system. So an activated sludge system is based on what is called MLSS, or the amount of biomass within the reactor. But because our biomass is on the media, we don't really speak of MLSS, because we speak of meters cubed of media, of meters squared of surface area that we have. So we don't really have what we call a typical MLSS, because we have a typical surface area in the media, or like, yeah, surface area loading rate for the application. So for MBBR applications, what are the limits on oil and grease and TSS in the influent wastewater? So as I mentioned, for TSS, that's a great question, by the way. For TSS, it is it can handle extremely high loads. So yeah, we've handled up to 1,000 in my knowledge, but I'm not sure if we've handled higher than that. TSS at inert, because as I mentioned, it just passes through the system because there's no filter. The stipulation we make is that it has to be small enough to get through the sieve so that it's not retained in the reactor, but that usually isn't a problem because the sieves are, you saw in the picture, they have pretty big openings. The oil and grease, however, we do have a limit on that. I believe it's like 80 ppm of free oil that it can handle, but I can get back to you on that one to be exactly sure. So it says, regarding the effluent sieves, how do we design for varying flows? Is there a potential problem with biogrowth on the sieves that would impede flow and cause water level fluctuations in the MBBR tank? So this is a good question as well. So the effluent sieves are designed for the peak and usually plus a safety factor flow rate. So we know how much water can get through the perforated holes. And then we design for what would be the max hydraulically to put through the tank. Is there a potential problem with biogrowth? So I can see why you would think that. However, the media is like a natural scouring because it's constantly rubbing up against the sieve. So it's constantly scouring the sieve, and then also we have an air scour, sometimes dedicated to the sieve, and then sometimes just having on the bottom of the reactor, we have air close enough so that the sieve is continuously scoured so that biogrowth doesn't develop and clog those holes. When using aeration to keep the media moving, is there extra aeration demand above what would be required for biogrowth? If so, what is the power demand and cost increment for this? That's a good question. So, so when the aeration needed for mixing is much less than that needed for the biological process in most cases. But it won't, because of the way the oxygen behaves, so to speak, like it bubbles out of the reactor, a lot of it does. So the oxygen that is required for the biological process is enough to keep the media moving. So you don't need, in a sense, it's not like moving the media doesn't consume oxygen. That's what I wanted to say. So it doesn't consume oxygen, so you don't need to like put more power into the system than you would otherwise. So for refinery MBBR applications, what is the expected biomass yield, i.e. pounds per day or pounds per TSS per pound of COD removed? So as I mentioned before, the bacteria themselves are the same regardless of what configuration the biological treatment process is in. So it would be the same as an activated sludge, or same as any fixed film or MBR, for instance. So usually it varies between 0.2 to 0.3, sometimes as high as 0.4 pounds, or you'd say like kilograms of TSS per kilograms of COD removed. Did the phenol and benzene absorb onto the media or sludge or converted? So we believe that this was taken up by the bacteria as any other form of COD does, because phenol and benzene are ultimately just a form of COD. And then it was used for energy and respired, just as any other form of COD. So we don't believe it was absorbed into the sludge or another place. What are the benefits of using MBBR versus SBR for sanitary wastewater? So SBR is a sequencing batch reactor, so it can, there's a large number of varieties. One of them is the ease of operation. That's kind of an obvious one, because an MBBR is constantly flowing into and constantly flowing out of, where an SBR is some of the time flowing into, some of the time flowing out, and in between there are different stages and things, and every cycle is different. Whereas an MBBR, the variations in load just sort of come and go, and then the bacteria are more acclimated towards it as well. Also, the MBBR tends to be smaller, because you most likely need more SBRs than an MBBR. So yeah, they're asking, is there no sludge produced in an MBBR? So yes, so the bacteria are performing the same as they do in an activated sludge system, where they produce more bacteria, which we call sludge. It's solids, it's waste to the system, so to speak. What is sloughing off the media passes out of the MBBR into the solid separation and goes for dewatering. So I guess I don't mean to say that the MBBR bugs don't produce sludge, because they do, but what I'm saying is we don't have like a sludge return for an MBBR that would necessitate attention. Basically, you'd have to figure out how much would need to go back into the system and to keep a certain concentration, and none of that is necessary for an MBBR. The sludge just passes out of the system and goes for dewatering. What is the typical dissolved oxygen target in an MBBR with activated sludge? So I think you're referring to a BAS system. So the MBBR, it depends on what it's doing. Presuming it's doing COD removal, we'd aim for 2 to 2.5 ppm of DO in the MBBR reactor. And I expect the same, except if you're doing nitrification in the activated sludge portion, you might want as high as 4 ppm. And if you get 6, you would have even a more efficient process. So it would have to be based on like the cost benefits of having a higher DO for the activated sludge system. How are the sloughed off solids handled? So as I mentioned, that when the biomedia moves and the biofilm sloughs off to sort of remain thin, the solids flow out of the system. So they flow through the sieve fine and out of the system. And there's a variety of ways to remove them. So one of them is a DAF, because bacteria are naturally a little bit lighter than water. They like to float. So a DAF is a very common process used. You can also use an ActiFlow. It takes some chemical treatment, and you can make them sink also. Or it can be in a conventional clarifier. So there's a variety of ways you can handle the solids. Or a disc filter if the MBBR isn't producing a ton of solids, then a disc filter has been an effective option as well. How does MBBR recover from a high oil breakthrough? Right. Would the sludge age be a result in the system and not a parameter controlled? So yeah, this corresponds to what I was saying before about the MLSS, that the sludge age would, we don't really speak of sludge age, just like we don't really speak of MLSS, because the biofilm is on the media. So it's hard to say how long it stays in there because it's, some of it is sloughing off and some of it isn't. So, so it's not a parameter that is controlled to or even considered in the design. So I think the final question is on the use of pure oxygen versus air. So this would be the same in any biological process that pure oxygen would improve the efficiency of the oxygen transfer simply because there's more there. But air is usually cheaper. So that's why it's used much more frequently. And then what are the temperature limits of the operation? So there are actually, that's one of the benefits of MBBR. It can run at a little bit higher temperature than activated sludge can. So yeah, so we say to about 38 degrees Fahrenheit. Yeah, is like the highest design temperature we'll start at. So that's all the questions we have. So an MBBR handout is available on the right in the handouts toolbar. Thank you everyone for joining and all your good questions. And please remember to take this brief survey at the end.